Also, as of today, as of this morning, we still have 70,000 core hours left. Great job, everyone, on burning those hours. We started with 200,000. And in the beginning of the week, that's what we had. The account will be active until August 31st. That's your Cheyenne account. However, the special reservation code that we have been using will expire today at 5 p.m. Mountain Time. So just remember that if you have an existing case that you want to rerun after 5 p.m., you're going to have to change the job queue. And this is the command. You can either use the regular or we can use the economy. And we talked about this. That's the very first CESO lecture on the different queues. Economy queue will be using less hours. If you use the regular, that's kind of a, if you think of in terms of money, the economy one is the happy hour. And yeah, so please remember to change that if you are going to rerun an existing case. Otherwise, I will go ahead and I will change on the sandbox to using the regular queue. Since you've already participated on the tutorial, you will no longer be eligible to join future tutorial. However, there are many ways you can still get engaged. One of which is by joining the many working groups that are available within CSM. And the way the working groups are designed, we have the co-chairs, which they define and lead the scientific directions of the working group. Then we have the liaisons, the scientific ones, which are the first point of contact for questions regarding science performed on the working group and questions related to the model components in general. And then you have the software liaisons, which are the primary goal is to help with software related issues for a particular component. So we have about 12 working groups right now. You can click on this link and see all of them and get engaged in the one that you're most close related, your research is most closely related with. We also have many activities and resources available to you. We hold 2 annual meetings in Boulder related to CSM. So normally the one in the wintertime, it happens in February and it's smaller. And then we have the annual meeting, which is in June, summertime, and that's like the big meeting. And that's where you can make connections and start new collaborations. So these are, you can click on this events page and you'll be able to see all the coming events and also the past ones. And that's a great opportunity for you to present your work in a CSM workshop and get help with CSM related things. You can also sign for the participants list and the working group email list. So that's these 2 CSM participants. And the link is here as well for you to click and sign up for these email groups. If you have trouble doing so, please let us know and we will point you to the right direction. As I mentioned before, you also have the CSM forums. There is a forum for each component, and there's some forums that's like cross components, and that's the best method for getting help with a problem that you face from now on. So if you run a case and you run into a problem and you see that it's like the ocean model, go to the CSM forum, go in the ocean model part, and then post a question, and you try to answer as fast as possible. Since your account will end at the end of the month, and the allocation for the tutorial is also ending once we finish these 70,000 or so remaining hours, there are ways for you to get an allocation on Cheyenne. And CESO has a web page that explains the ways for doing so. If you are in a US-based university, it's relatively straightforward. So just click on this link and then check out the instructions there. And again, if you need help, please feel free to reach out to us. For today's office hours will be slightly different than on the previous days. We will split the groups by components. So we're going to have an expert for each component on these groups, or more than one actually. And we have 4 groups. So we have one just for land ice. So Gunter will be moderating that one. Then the second one, we combine ocean sea ice and BGC. The third one is just the land model. And then the fourth one is HEM and WACM chemistry. And the way it's going to work out, again, we're going to have a breakout room for each of these groups. And there will be other breakout rooms in addition to that one where people can go for a one-on-one interaction. And we can use that the same way we've been using so far. And you can join any of the breakout rooms at any time. And then I want to, again, thank everyone that was involved in this tutorial, starting from the committee, myself, Alice Duvivier, Cecile Hane, Gunther Ligui, Peter Lawrence, Adam Phillips, and Christine Shields. Logistics, a huge thanks to Elizabeth Faircloth for everything that she has done throughout this week and before, and will be doing after. Education outreach, that was the first session we had a few weeks ago with Val, Sloan, Jerry Sycon, and Elias Mason. The VG for the computing support, web support from Ryan Johnson. We had over 60 staffs involved throughout the tutorial, and you've met most of them, from software engineers, scientists, and logistics related. Funding from NSF, and then finally to all of you for participating. And we really hope that you enjoyed this week and you got what you came here looking for. And we still have one day to go, so I hope you enjoy today as well. We'll see you soon in any other CSM event. And again, don't hesitate in reaching out to myself or Elizabeth if you have any questions related to anything from CSM. And with that, it's now 8:50 a.m. Mountain Time, and we're going to start the Q&A hours for today, and I'll pass the floor to Alice Duvivier, which will moderate that session. Alice, please go ahead. Introduce yourself.
Hi, so my name is Alice Duvivier. I've been at some of the office hours, but I think I probably haven't met most of you so far. I'm moderating this session. I'm gonna just do a quick introduction of all the people who will be, all the CESM experts who will be providing feedback. So like I said, my name is Alice Duvivier. I'm a project scientist. I work on polar climate, mostly sea ice, and I've been at MPAR for about 5 years. So I'll call on the people. So next, we'll stick with the sea ice theme. So Dave Bailey, can you introduce yourself?
Sure. So I'm Dave Bailey. I'm going to be leading the ocean ice breakout this afternoon, and happy to chat with you in the session coming up.
All right, next, Betty.
Good morning, or afternoon, or evening. I'm Betty Otto Bliesner, scientist in CGD, and I work on modeling past climates.
Thanks. Zhang?
Hi, everyone. I'm Jiang Zhu. I'm a project scientist at Paleo and Polar Climate section. I work with Betty on similar topics, paleoclimate simulation.
All right, Bill Lipscomb.
I'm Bill Lipscomb. I'm also a scientist in the Paleo and Polar Climate section, and I work on land ice modeling.
And then finally, Gunter, I think I saw you on here. Nope, he's signed off. Never mind. Oh no,
Gunter's here.
I'm here, but I'm just here for watching. But all right.
He may chime in.
Maybe. So good morning, everybody. I'm Gunther Legge. I'm the science liaison for the land ice working group, and I work with Bill Lipscomb on land ice at Anchor.
All right. So I think we're going to start the session with some questions just to gauge your previous knowledge, I guess, of the polar, either land or sea ice and paleo components. So Elizabeth, if you're able to start those questions for the poll.
Elizabeth, does everyone know how to do the poll? I'm not sure I do.
I think for the co-hosts, we just see the responses. And it looks to me like it doesn't record until someone's answered all 5. So I think that's why there's this long pause where it's like.
I
That's
understand.
exactly true. It does seem like awkward silence and dead air. Yeah. I can see that 2 people have completed it so far.
When we get up to about 30 people completed, so that's 3/4, then I'll go ahead and start this. But the point of these questions is to kind of start a discussion. And it doesn't matter if you know a lot or a little about them. I just want to emphasize that. So we're getting closer. We have about 10 people left. All right, I think we're probably at that point. So if you want to end the poll, Elizabeth, and show the results, I think we can just use these as a start off point for this discussion. I want to ask people, it looks like we got 1 question ahead of time in that poll END. So I'll ask that one first after this little discussion. But if you have additional questions, please put them in the chat and I will ask them live so that everyone can hear. And then the appropriate experts will respond to those. All right. So is everybody able to see the response for the answers? Is that right? Okay. Dave's nodding his head. Great. All right. So the first question was about land ice and which description best describes the current state of coupled land ice modeling in CESM. And it looks like about 52% of people said the surface mass balance, that's SMB, is computed in the land model. There's an interactive Greenland ice sheet and an interactive Antarctic ice sheet in development. That is the correct answer. It looked like a lot of people also thought the dynamic ice sheet model is run offline with the surface mass balance computed in the land model. So Bill or Gunter, if you have other comments about responses to this question, I invite you to go ahead and say whatever you want at this point.
Yeah, I'll chime in. Number 1 would have been the correct answer around 2010 before we had CESM. And number 2 would have been the correct answer for CESM 1. So if you were answering that question 5 years ago, that would have been correct. And that is still a way that the models often run. But if you're interested in coupled land ice modeling, the current state of the art for CSM is question 3. As for question 4, it would be great to have all land ice components fully interactive eventually. I don't know that we'll ever compute surface mass balance in the land ice components themselves because it works so well to compute them in a land model.
Great. All right, so then the second question was kind of a contrast between sea ice and land ice. So what's the main difference between sea ice and land ice? And it looks like most people said land ice is fresh while sea ice is saline, which is the answer that we were thinking of as well. So land ice is like the ice sheets on Greenland or Antarctica, and it's formed from precipitation that compacts, whereas sea ice is frozen seawater. So there's a little bit of salt. It's not as salty as the ocean, but there's salt in that matrix and it makes them behave differently. Part 2, land ice doesn't move while sea ice does move. In fact, both land and sea ice move. Sea ice moves on a much shorter time scale than land ice because it's moving around in the ocean and pushed around by the winds and moving around with the currents. So it moves pretty quickly, but land ice does move. It's just a lot slower. And so that's also addresses the third part of this question, land ice evolves on shorter timescales. In fact, land ice evolves on much longer timescales than sea ice, but both evolve on longer timescales than, say, the atmosphere. All right, I'm going to go to question 3 now, sea ice, so which is not a parameter that can be used to change the sea ice albedo. Dave, do you want to comment about this one?
Sure. So the current scheme that we have in the sea ice model is this delta Eddington radiation scheme. And so there are certain inherent optical properties that we are adjusting, but then those effectively end up producing the amount of absorbed shortwave in the snow and the sea ice, as well as the effective albedo that comes out of it. So, so when you look at this, I mean, you'll see this afternoon in the exercise too. The dry snow grain radius is actually one of the most used parameters that we use, because what happens is when you reduce the size of the dry snow grains, that increases the albedo, and when you increase the size of them, that reduces the albedo. So it's sort of inverse, and that's actually our number one parameter that we will adjust. Sometimes it's necessary to go beyond that, and so we will actually adjust the melt onset temperature, and so that means that that's the point at which melt begins. Typically, it's somewhere between -1 Celsius to 0 Celsius is the range that we use. And so, but you know, it varies by region and time of year and so forth. And so we often use that as another parameter to adjust. And then a third one that we sometimes adjust is the maximum snow grain radius. And that just means when you've achieved that melting point at 0 C, what is that maximum snow grain radius that you're going to get? And, you know, it can be 2,500 microns or 2.5 millimeters. So it's pretty big. Anyway, but then the final one, and that was kind of the tricky one, which most of you got, which is, or responded with, which is not the right answer, is, is the right answer for this, because we asked which is not. So good job. Snow conductivity is, in fact, something used in the thermodynamics, but it's not used in the radiation. So snow conductivity doesn't actually impact the albedo. So number 4 was the correct answer, and nice job.
All right, great. I see there was one question that came in at that point. I'm going to save that for the live discussion in just a minute. I want to go ahead and go through these questions so we don't get totally derailed on one topic or the other. So the 4th question is paleo. If you wanted to run an ice age climate simulation, so that means 5 to 6 degrees Celsius cooler globally, starting from a pre-industrial climate, which model component would take the longest to reach equilibrium? And it looks like most people said the deep ocean, and that's right. So the atmosphere, just for reference, spins up or becomes equilibrated on an average of about like days to weeks, depending on what you're looking at. The land carbon cycle, I think that does take a while as well, but not as long as the deep ocean. The deep ocean takes hundreds to thousands of years to really equilibrate. And Arctic sea ice takes like 50 to 100 years usually to equilibrate. So if you wanted to run this, definitely the deep ocean is kind of the limiting factor in how much you're going to need to spend in computer resources to spin up. And then the last question is paleo specific. So what's the correct way to set up the Earth orbital configuration for a paleoclimate simulation of the mid-Holocene, which is about 6,000 years before 1950? Either Betty or Zhang, go ahead and comment on that one.
Okay, maybe I will take this one. I'm sorry, I cannot see the pool results right now, but I know they.
Oh, it looks like, so 7% said specifying the orbital year, 21% said specifying parameters for eccentricity, obliquity, and precession in the fixed parameters mode. No one said specifying solar insolation, 52% said either of the first two, and 21% said either the first or the third.
Okay, it's good that no one selects the solar insolation option. That's not the correct answer. So there are multiple ways you can set up the orbital parameters. So because orbital parameters are largely deterministic, so for the past climates in millions of years, so you give us the model year, the time period of your simulation, we can calculate the orbital parameters. So there's one way you can do that is to tell the model the simulation years you want to do. Then the model can calculate the parameters on the fly. And there are other ways. For example, you can set up the parameter values for each orbital parameters. Then you get a configuration you like. So those are for time periods with fixed orbital configurations. If you want to do a simulation, a transient simulation, for example, for the last deglaciation, so in that case, you want the orbital parameters to vary with the model years as the simulations advance. In that case, you can change the orbital parameter mode. There's a parameter called ORB mode. So you can change that to variable years, and then you can do transient simulation. So in this case, again, there are two correct ways to set up this mid-Holocene simulation, either through fix the orbital year or through fixing the values for the orbital parameters.
Great, thank you. All right, so, and sorry if I cut anybody off who had been almost done answering, but the poll ended early. So I'm gonna go ahead and move to the questions. The first question, I'm going to go ahead and take it from the chat because it was something we talked about today, and then we'll move on to the one that got asked early. So Vicky asked regarding the sea ice, is it the same range of snowmelt temperatures that the land ice uses? Dave or Bill?
Yeah, I'm waiting for Bill to chime in on that one. You know, we derive the melt onset temperatures basically from field campaigns in the Arctic. And so those were sort of typical values that we would see in the range in the Beaufort Sea, for example. But we did not at all coordinate with the land ice people. And so I'm not sure how you guys set it.
I might be missing some background. What exactly is meant by the same range of snowmelt temperatures?
Well, so I said, you know, from -1 to 0 is sort of when melt onset starts.
Oh, right.
So is that similar for the land ice, or?
I think it's similar. The land ice, the snow model for the model for the snow that sits on top of the land ice is actually the snow in the land model, CLM or CTSM.
Oh, right. Yeah.
So it would, for historical reasons, the snow schemes in the land model and the snow schemes in the sea ice model have not been identical. Also because it's just snow just behaves differently when you're sitting on top of an ice platform on the ocean compared to a land surface. But those schemes have been, I think, converging a bit through the years, but they're two distinct schemes.
Right. That actually leads nicely into the other poll question, I think.
Yeah, about what's different about sea ice and land ice, and one of those big things is salinity. So on sea ice, not that we don't take all these factors into account, but when Bill said snow behaves differently on like sea ice versus land ice, one thing that can change is that some of the salt from the ocean can get into the snow that's on top of the sea ice, so the snow becomes a bit salty, and that can affect things like satellite retrievals and stuff as well, and that's beyond what we need to talk about here. Mm-hmm. This also dovetails well with the question that was asked on poll ENV, which is, and I don't know who asked this, but are there any planned developments for snow modeling and processes in CESM? And they didn't specify a particular component, so I think this is open to land ice, land, or sea ice. So if you know of anything, I think this would be a good time to just talk about changes to snow modeling.
So I'll guess I'll start. So as Bill alluded to, the land model snow treatment has sort of evolved separately from the snow treatment on sea ice. And as far as I'm aware, I don't think CLM5 has any really new fancy snow developments going on there. They've had windblown snow, compaction of the snow, and wetting of the snow features in there for several years, I think. But one of you, Bill or Gutter, can correct me on that. In terms of the sea ice, we've always had sort of a constant density snowpack. We don't account for blowing snow. We just, as Bill said again, we have the complexity of the snow is moving around with the sea ice. And so it is a very difficult thing to sort of keep track of. So any new variable you add for the snow has to be carried around as a state variable too, and advected with the sea ice and so forth. That being said, just yesterday, Elizabeth Hunke just issued a pull request into the SEIS consortium for brand new advanced snow physics treatment. And so this will introduce a new snow tracer into the SEIS model. Now, this is not exactly the version that we have in CESM currently, but it will be one that we'll be using as of CESM 3 in a few years. So.
I'll just add that although the treatment of snow in the land model is pretty sophisticated, one thing that's on the land ice wish list is blowing snow. Since it's been shown, and for instance, Land Ice Working Group co-chair Jan Lennertz has worked some on this. In regional models, it's been found it makes a difference when snow is to the surface mass balance, if snow is blown around from one region to another region. And that's something that we don't yet capture in CESM, but would like to.
All right. So one thing I forgot to say earlier too was that I would invite all the participants to go ahead and turn on your cameras so this can be more of a discussion. There are no other questions in the chat right now. So if you have a question, I would invite you to either put it in the chat or you can go ahead and raise your hand and I can call on you. It would be nice for us answering to be able to see people's faces so that we don't feel like we're just talking to black screens. If there aren't any questions, it's going to be a really awkward next 30 minutes while we all sit here and stare at each other.
I do like that you've got your name on the wall behind you there, Tim. So.
Nice. So this is going to be the topics of today. I mean, I do have some things I wonder about with size. I mean,
yeah.
you broke the ice now, so I can speak out.
Sure.
What is thermodynamically happening at the base of the sea ice, and the exchange with the operation layer? Like what is physically thermodynamically happening over there?
It's a good question. I mean, there's a lot going on, but I'm trying to get at some of the specifics of what you're looking for. But we exchange the fluxes of fresh water, heat, and salt at the base. And so this happens during growth and melt. And so you can have positive or negative fluxes depending on whether you're in a growth period or a melt period. Traditionally, we're actively working on this. Alice has a paper, hopefully accepted soon, talking about the way that we've traditionally done the salt fluxes in the model. We've always sort of naively assumed that the sea ice was 4 PSU, and we used that for our flux calculation. It simplified things. But the new thermodynamics scheme that we have, so from Adrian Turner, it allows for prognostic salinity. We have a freezing point at the base of the ice that depends on the salt. And so there's a lot more complex interactions going on. And so we're actively working on improving that flux exchange at the base of the ice with the ocean.
Okay, and how does it work with, like, if I mean, this is pure theoretically, but if you have like more thinking about energy or heat exchange, like if you have like a warm current or something flowing below your ice, like, or like
Right.
that doesn't.
Right. So we also couple momentum at the base too. But yeah, basically at the bottom of the ice, there's an energy balance equation that's solved, whereas the growth melt is equal to the amount of heat coming from the ocean, but also balanced by the amount that's conducted away from the base. And what happens is if you're conducting more away from the base than you're actually getting from the ocean, you're going to have growth. Whereas if you have more heat coming from the ocean than is conducted away, then you get melt. So that's sort of the simplistic view, at least at the bottom of the ice. So
Great. So we have a follow-up question here from Rudra. Do you want to ask your question live, Rudra?
Yeah. Hi, everyone. So recently I read a paper in which in situ observations were used for determining that how Arctic cyclones and the following processes may affect the sea ice loss in the Arctic, right? So they mentioned that the observations and the results were pretty accurate as they use very small spatial scale, whereas in model, huge means comparatively larger spatial scales are represented, right? So how accurately the oceanic activities beneath the sea ice, such as heat transfer between subsurface ocean and sea ice, or the mixing layer depth, or the Ekman pumping. So how accurately are they represented in this CSM or sea ice model? Thank you.
Alice, do you want to take that one?
I can start. So I think the answer is we know that like the mixed layer depth, for example, is we probably don't have high enough ocean resolution to really adequately resolve it in some places. And they're especially in polar regions or the Arctic where you get different sorts of stratification because of the freshwater lens at the top and stuff like that. We don't necessarily have all those fine details in the ocean model. So I would say that because of the large scale and also because of, vertical resolution as well as horizontal resolution, there are going to be some inadequacies compared to like observations of those sorts of features in the real ocean. We also know because of the coarse horizontal resolution primarily, we don't resolve coastal currents super well. So like around Antarctica or places around the Arctic, if you're interested in how the coastal currents are going to affect the sea ice near places where people live, for example, those are not going to be super well resolved. And one thing that is now in the SICE model, but we don't have in CESM2 yet, is land fast ice. So you can get sea ice that in an area where the shoreline is pretty shallow, the ice can be thick enough that it basically wedges into the bottom of the ocean and then it gets stuck. And so that's land fast ice. And that's pretty important actually for a lot of settlements in the Arctic. And it can be important as well in the Antarctic for biology and stuff like that. Like penguins use land fast ice a lot. So we do have that in CICE and it will be in CESM3, but it's not in CESM2 right now. So I think one thing you just have to accept with any sort of modeling is that you're never going to quite resolve all the processes or all the features that are going on. You can always go to a finer vertical or horizontal resolution and find something new that you're not going to resolve. And so I think we do a reasonable job, but I do think there are probably some inadequacies there. All right.
Thanks,
So,
Alice.
yes. So there's a question from Cheng Hao. I'd like you, if you're willing, to ask this yourself.
Yeah, sure. Well, actually, honestly, I'm not a ocean scientist. I was just wondering because I found in the lecture you are developing some biogeochemical component and also water isotopes in CESM in sea ice. I was just wondering what kind of biogeochemical process will be included in future release versions. Thank you.
Dave probably knows more. So I was going to say one of the things that's new in CESM 2 is that we have this prognostic sea ice salinity, which means the salinity throughout the column of the sea ice changes over time. In the past, we just had some fixed profile and we said, this is what it is everywhere, but that's not really how sea ice works. Another reason that that was important is that having a prognostic salinity is relevant for biology and biology that like lives in the ice strata. So I would say this is a development. I'm not sure who is working on this directly for CESM right now. I do know that CEIS itself has the capacity to look at like, you know, phytoplankton and including like diatoms and stuff like that within the ice column and looking at like different nutrients. So this is more like I've looked at the code and seen these aspects, but I haven't worked on it personally. Dave might have more insight though.
Yeah, I haven't worked on it personally either, but I know that Nicole Jeffrey at Los Alamos National Lab is, she's actually working on the full column biogeochemistry, which will be available in the next release of the CEIS consortium model, which again, as I mentioned, is not going to be available in CESM until CESM 3. We're developing it currently. And so this contains numerous BGC tracers within this, and it is the full column. Currently in CSM 2, we have what's called the skeletal or just bottom layer BGC in there. And so there is the possibility of doing some like primitive coupling with the sea ice in the ocean, but we have not really explored that. And you know, Keith Lindsay from the Biogeochemistry Working Group we've been talking a lot about trying to do some experiments where we're coupled with the marble ocean biogeochemistry component and try to make sure we get those exchanges better represented. You know, and we would try to do it mostly from the marble centric perspective. So what are the main species and components of that model that we could also simulate in the sea ice? And so it's very active sort of work, and we hope to have something within the next couple of years on that.
Great, thanks. I see that Tim says he has a follow-up question, so go ahead and ask your question, Tim. And then there's someone else after that. So Tim, go ahead, and then Ben, you'll go after him.
Yeah, sure. Yeah, I was chewing a little bit within my head with the fact that you, I think you explained right away that sea ice, when it moves into the land, it kind of becomes grounded, so to say, like land trust ice, you call it. If it's large enough, like theoretically, it could change like the sand that blow or whatever, like the sea ground below it, like a ripple it a little bit onwards. Is it represented or?
I understand what you're asking, but no.
And also, if the answer is no, and the answer is no,
right,
could you do that?
Yeah.
Or can you do that?
I mean, I think that there's talk, again, this would be development, but there would be talk about some sediments from the grounded ice getting trapped within the ice and being carried around, because that sort of sediment iron can be very important for the biogeochemistry cycle. But it's, again, we cannot represent that at this point explicitly, but it is something we hope maybe in the next 4 to 5 years. So
I also want to bring up for Bill, hopefully he can elaborate on this some, but right now at the face of a glacier for example. I don't think we have ice shelves. And at the face of a glacier, we don't really represent calving. We have like an iceberg, for example, we just have like fluxes that just go in entirely to the ocean. And so it's not exactly like an iceberg, but Bill might be able to comment on either potential, what the state of that is now, and then what potential developments there are, especially with the new upcoming ocean model, where we could have potentially changing ice shelves or glaciers at the interface with the ocean.
Sure. Well, a big thing that's coming, which you've heard about, is MOM6 replacing POP. And POP, you may have heard, when you get to the ice shelf, POP doesn't have any cavities under the ice shelf. It just has a wall where the observed shelf edge is. Whereas MOM6 has the capability to circulate the ocean underneath the ice shelf and back out the top. And in some cases, for example, underneath the big Ross and Filshner-Ronne ice shelves, you actually have marine ice being deposited at the surface of the ice shelf. Because we haven't had an ocean model that can do this, we haven't worried about this, but it's something that we'll be talking about how to handle in the future. Another thing we'll be talking about is when you have ice shelves advancing and retreating, the land ice requires a surface mass balance from computing the land model. And so that means that the boundary between the land and the ocean has to change in some sense, or rather the overlap region between the land and the ocean has to change, because the floating ice is like part of the land model and the sea beneath it is part of the ocean model. And so that's an upcoming software engineering challenge to allow all that to change dynamically.
Great, thanks. So Ben, you said in the chat that you have a question, so go ahead and unmute and ask your question.
Sure. Yeah, so it's maybe a bit specific, but I know that historically, like most CNET models have a lot of trouble simulating sort of realistic polynyas, like sort of open ocean polynyas in the Libau, like the Maudrais polynea and the big ones that sometimes happen in addition. And I know there's some papers recently, because I was just looking at it, that use CESM at a high resolution and it works a lot better. But I'm wondering, I guess my question is sort of like, how do you expect that to change as with resolutions and also with changing like an ocean model? Does that kind of throw a lot of stuff out the window? I don't know if anyone like that's sort of specific. Yeah.
Do you want to answer, Dave, or do you want me to?
Yeah, I have a strong opinion on this. So, yeah, open ocean polynyas are an interesting challenge because they are really ultimately the interaction of local winds, but also mixing of warm waters from below in the ocean. And so you just have this confluence of events that happens. The real problem, the real challenge with these things is, you know, in the observed sea ice record, we have seen 2, 3 Weddell Sea polynyas, you know, and so they're not very common. And so the thing is, it is, you know, I think it's fair to say that the coarse resolution models don't really simulate them. And that's true. And it's probably because the resolution is not fine enough in the ocean to really resolve that sort of topographic upwelling that is leading to those sort of events. That may change with MOM6 because we're going to go to a sort of a standard resolution of 2/3 of a degree instead of 1 degree. So maybe that would be sufficient, maybe not. However, the reason I have a strong opinion on this is I feel like the high res, the 1/10 of a degree, goes too far the other direction. You know, what you see in those high resolution runs is you see Maudrais polynyas like every 10 years. You know, they're almost like clockwork. And this is in an 1850 sort of cold climate. So I find that kind of unrealistic in my opinion. Although, there's people who've debated on this. We don't really know how often they might have occurred in 1850 or whatever, but there is a paper by Frank Bryan and Peter Gent that shows that the high resolution tends to have too much poleward heat transport in the ocean. So you're probably getting excessive heat into these regions, and that's what makes it much easier in the high res case to form these open ocean polynyas. There's also a subtle distinction about the definition. Are you just seeing basically the Weddell Sea circulation coming around and then closing off, and all of a sudden you have this big hole in the middle? So there's some interesting debates on this. And I know that a lot of people working in particular on this IHES project, which I think you're referring to, they get very excited about the polynyas in this. And so, but anyway, that's sort of my 2 cents worth.
I'll chime in here, not about the Weddell polynya. I know you asked that specifically, but one thing we have noticed in CESM2 compared to CESM1 is that there's a lot more open water ice production, basically, which we call fragile ice production in the model in CESM2 compared to CESM1. And a lot of this is in coastal regions. And so there's a lot of ongoing work right now by myself and others at NCAR and not at NCAR to understand what exactly is going on. Like, are we getting more polynyas, or is it just like a shift in processes that are going on in the model and we're not actually seeing a change in polynyas? So I would say that's kind of an area of open research. We do know that in the standard, not high resolution version of the model, as I mentioned before, like, we don't adequately simulate coastal currents, and we don't adequately simulate winds, the downslope winds that drive most coastal polynyas. And so there are going to be deficiencies, but at the same time, if you want to look at how polynyas or coastal ice might change over time, this is really one of the better tools that you can use, because most high resolution simulations don't go forward in time very much, or there aren't very many ensembles because they're just too expensive to run. So, all right. I think that's all of the questions that are in the chat. I don't see anyone's hands up, but I would invite people to go ahead and put your hand up, or, oh, we got one in the chat here. Charles, do you want to go ahead and unmute yourself and ask yourself?
Yes, I'm looking at the surface behind you, and I was wondering, is that a typical sea ice surface, or, the ice sheets, I believe, are thick and blocky and cover the entire sea surface, or do you treat that surface behind you as a regular ocean surface from the radiation point of view? And how do you know where those kind of surfaces exist in the ocean?
Right. Okay. I'm going to pin myself, which feels really weird. And I don't know if I know how to I know how to unpin. So what you're seeing behind me is a picture of sea ice. This is what you'd call pancake ice. It's from the Antarctic. And what we do in the model is, for each grid cell, we would look at a picture like this. For example, imagine this is a grid cell behind me. And there is a ice thickness distribution. So you could imagine that one of these bigger flows, these are actually pretty small. They're maybe not quite this small, but they're not giant flows in this picture. But you could imagine, you see there are different sizes of these flows and they're different thicknesses. So we do model the distribution of thicknesses of ice within a grid cell. And we also model the percent of a grid cell that's covered. So you could say, for this grid cell, I might say that 2/3 of it are covered with ice. And so the concentration, the bulk concentration would be, like 0.66, which is the concentration of sea ice in this grid cell. And then within that, we'd say, okay, what percentage of that concentration is this thicker ice versus maybe like this thin, small ice. And this, as I said, this picture specifically is pretty small scale. So this is much smaller than what we look at in our model, but this sort of thing exists as you go up in scale as well. So yeah, and then, we, for each one of those different thicknesses, we calculate the heat fluxes, and we calculate the snow. You can see there's more snow on these thicker flows compared to like a thin flow. And so we go through and we calculate all those physical processes, by the thickness type of ice, basically. All right, I'm gonna remove my pin. Hopefully that made sense, Charles.
I was going to add on to that.
Go ahead.
The other key thing about that picture behind Alice, so you think of all of the sea ice pieces there, they're sort of all grouped together into a grid cell, and they're all simulated by the CEIS model in the CESM. So the CEIS model has its own albedo treatment, surface flux treatment, everything. All of those dark patches are ocean, and they're actually simulated by the POP ocean model in CSM2 and will be simulated by MOM6 coming into the future. And so again, the POP model has its own surface flux treatment, its own albedo treatment. It's not a very sophisticated albedo treatment. It basically just sets the albedo of all that dark area to 0.06. But then you for each grid cell, there's a fraction of open water and there's a fraction of sea ice cover, and the open water part is simulated by POP and the sea ice covered part is simulated by CEIS.
Thank you.
All right. Again, I don't see any questions yet in the chat or raised hands. We haven't had any on paleo. So if there's anyone who has any questions about paleo, this is your chance. You have both Betty and Zhang here who can answer your questions. I will be perfectly honest, the poll question about how you set paleo simulations, I had to look that up because I don't know a whole lot about paleo. So, All right, we do have a hand up.
Yeah, hi.
Yeah, go ahead.
Yeah, I actually do have a question about paleo for either Zhang or Betty. So CSM, when you're developing it, you're basically validating it against historical simulation or historical records, the instrumental record, right? So I was just wondering what you actually use, what kind of data sets or whatever to make sure that the CSM that was validated for running kind of modern climate can accurately simulate these paleoclimates, LGM or the Pliocene or, however far back.
I'll let John answer that because he has been working a lot on this for CESM2, looking at the last glacial maximum, which is 21,000 years ago, and also warm climates like Eocene 50 million years ago with high CO2. So would you like to expand on that, John?
Yeah, sure. So I think firstly, if you compare the different model components, maybe a atmosphere is making a biggest change, say, in this context for the development from CSM1 to CSM2. So most of the change is from the atmosphere component. So when you evaluate the model against observation, so usually people do atmosphere only simulation first. So you use prescribed observation of sea surface temperature and sea ice to force the atmosphere model. So you compare the simulation, say the precipitation, cloud radiative forcing, etc., against present day to say how do you simulate those variables. So after you are satisfied with the overall simulation, you do fully coupled simulation. So for example, you do pre-industrial simulation with everything set as a pre-industrial. And in this coupled setup, you will also look at other components. For example, how much sea ice cover you get in the Arctic, is that overall realistic, and the sea ice thickness, and also the ocean subsurface temperature. Then with this pre-industrial simulation, more or less spun up, so close to an equilibrium state, you can move forward to perform historical simulation. So starting from 1850, so you put a transient forcing into the simulation, including aerosol emission. Then you can perform this transient historical simulation. That's really, I think, very important here because this simulation enables you to compare with the satellite observations more closely. So that's exactly the same time period with the same aerosol forcing, greenhouse gases, etc. So you can take a closer look at the historical simulation. And for different model components, there are a lot of people looking at their own model components that they are interested. So there are a lot of eyes looking at the simulation and to examine the variables they are interested in. So if there's a problem, for example, if you have too much sea ice cover over the Labrador Sea, then we know there's a problem. So we need to diagnose what's going on, what went wrong there, and we can make changes, make improvements from there.
Great, thank you.
John, do you want to also talk about what kind of paleo records we use and some of the new techniques for working on those?
And I was going to add, because Tim mentioned it earlier, can you say something about the water isotopes and where they're at in CESM2?
So, okay, I will talk about the water isotopes first. So the water isotopes currently, it's only in the fully coupled CESM 1.2 or 1.3. So in fully coupled CESM2, we don't have this capability. And this is really unfortunate, but we are working on that. Hopefully we can get this capability online with CESM2 later. So this is particularly important for paleo. So if you look at the paper from your advisor, just Tierney, so your group put together the proxy SST, say, for the last glacial maximum and ice age climate. So it's a cold climate. If you put together the high quality sea surface temperature data, more than 60% is actually isotope records. So you can see that if you want to really take advantage of this paleo information, then this isotope capability is crucial. So go back to the Betty's suggestion. So for paleo, we have this proxy reconstruction of temperature and also maybe precipitation. So those can be used to evaluate model. And of course, the spatial coverage and the availability are in general limited, but you can still get some idea. For example, for the ice age climate, if we can get 1,000 proxy SST records, we can have a more or less idea about how cold the climate is. And you can also take one step further, use the advanced technique like the data assimilation to combine the information in proxy and a model to get a better reconstruction of the global temperature, precipitation with some uncertainty. And those information can be used to evaluate the model. Usually the first thing I look at is, okay, the bulk number, how cold the ice age climate in proxy and how cold the model simulation is. This very simple number can tell you a lot. And if you are interested in further details, you can look into how the sea surface temperature is distributed. That gives you finer details and additional metric about the model performance.
Great. And I want to point out too that Ryan put in the chat the link to the paper that Young just mentioned. I think we're closing in on the time. There's one last question Jean-Yu, do you want to ask that live?
Yeah, thank you. My question is regarding to the lecture, like there's a plot comparing the ISAT observation of the eye thickness, comparing with the model simulation from the WorldCam and CAM. And I see there's a little bit large discrepancy between them. I'm just wondering, like, when you see a this difference between observations and model, which variables that you think is important to causing this difference in the model, and how do you find it out from when you analyze the models? And yeah, that's my question.
Okay, so Dave put a link to a paper that I led on this sort of question in the chat. But for this instance, with looking at the ice, and actually this is not too dissimilar from what I would do if I were looking at the atmosphere or something like that, is when you see something that's not what you expect, I start looking at some of the processes. So like I looked at energy budgets and I looked at mass budgets between WACM and CAM and tried to figure out how those were different. And then in this particular case for CESM2, it wasn't necessarily a discrepancy from observations, but a big difference between the models that we weren't expecting. And then also, that then can relate to a discrepancy with observations. I found that like the surface melting was really different between the two. And so then I think about, okay, well, what's different in the model in the surface? Like what would cause differences in the surface melt? They're using the same snow scheme, so that can't be it, that sort of thing. And in this particular case for the paper that Dave linked, we found that the atmosphere was really different. And so I think it becomes a little bit of like I don't want to say a goose chase, but like you find one little piece of something that might be a nugget that helps you get to the answer, and you just kind of keep following that trail. And sometimes you do that and you get to a dead end and you're like, I really have no idea, like that wasn't the reason. And then you kind of have to step back and think, how else can I do this? And I think that's a lot of just a scientific process that probably most of us go through. If any of the NCAR scientists know, a priori what your results are going to be, then go ahead and chime in. But usually for me, it's very much a discovery process. And the longer you go on and more you work with models, I think you get a better intuition for, okay, this might be a culprit for this. And so you can kind of start on maybe the right path, what appears to be more easily. But there's still things that, even for those of us who've worked with models a long time, I mean, I've worked with models for now like almost 15 years, and Dave's probably worked with models for a lot longer than that. And I'm talking about sea ice models specifically here. But then you get something like with CESM2 development, this is not a secret, there was a big problem we had with the Labrador Sea freezing over. And we did this sort of thing where we tried to investigate fluxes and we tried to investigate, all the things that we thought might be causing it. And we kind of we still don't exactly know what the culprit is. But it's just a process. And it sounds like it looks like Betty linked a paper where Zhang did the same sort of thing for the LGM in the chat as well, if you're interested in linking that. We are at 9:45. I think the session was supposed to end at 9:45, so I want to be respectful of people's time. One last question did come in from Rudra. So if you need to log off, we understand that makes sense. Rudra, if you want to ask this last question live, please go ahead.
Yeah, I was just wondering that in the CSM2 model, what role does the ice albedo and sea ice roughness would play in the outgoing and incoming long wave radiation? If we just if we ignore the cloud feedbacks, I know that cloud feedbacks are a major contributor in this thing, but what would be the situation? Thanks.
I'm happy to answer this one. I mean, I think if I understand your question correctly, the short wave and the long wave computations are completely separate. So the long wave computation has associated with it an emissivity, which is basically how much of the long wave goes up. And then you have incoming long wave from the atmosphere, and so you end up with a net flux of long wave. So we use a constant emissivity in the SEIS model. And so really, I mean, there are probably coupled feedbacks that would eventually lead to changes in the long wave, but just directly in terms of the surface sea ice, it's solely a function of surface temperature and a constant emissivity. So I don't see how the albedo would directly impact that. I mean, there would be an indirect effect, possibly. In terms of the sea ice roughness, similarly, we have a constant sea ice roughness everywhere. So the only thing that affects the drag over the surface is stability in the atmosphere above. And so that will change the exchange coefficients over sea ice, but the roughness currently is constant. And I think earlier there was a discussion a bit about the fluxes at the bottom of the ice and the fluxes on top of the ice. We are hoping to move to a more sophisticated form drag formulation, which will actually explicitly take into account roughness underneath the ice and above the ice as well. So, and I was going to add something a little bit to Alice's point, that when we do these long pre-industrial simulations, what we try to do is we try to find a balanced climate for 1850, and we try to adjust the sea ice parameters to sort of fit what we believe is the best sea ice conditions for 1850. And we did this for the Wacom simulations, and we came up with a set of albedos. And then the idea was we wanted to use the same parameters in the CAM style simulations. But it turns out with the CAM style simulations, the sea ice was much, much thinner. And some of the reasons for this are in Alice's paper, as I pointed out, and Alice has talked about. But then there was sort of this feeling that we weren't going to separately adjust those parameters for the CAM simulations. And so we sort of had to live with the thinner ice in the CAM style simulations. So, but it is a process when we're developing a model where we're trying to achieve a balanced climate for 1850, and then we can start our 20th century runs from that. So.
All right. Well, I think we are at time. We got some really good questions. So I just want to thank everybody for attending this. Thank you to the NCAR experts for providing your expertise. And we hope to see all of you guys as part of our working groups and into the future when you're doing whatever cool research and science you're doing as well.